Hi Wildcats, this is Unit 8 Focus Question 3 practice problems. We're going to run through Newton's three laws and how we can use them in different types of problems. We have a guest today for his first law. Newton himself has joined us. You can see some amazing artist has added on a hat here. So Newton is in his kitchen. We're actually going to be talking about ketchup. Though really I hear his specialty is apple pie, but I'm sure he was good with many different ingredients. So just a quick review, Newton's first law says an object will remain at rest or in uniform motion in a straight line unless acted upon by a net external force. And it also deals with this idea of inertia, that objects will remain in their state of motion unless a force acts to change their motion. So the same thing, inertia is really just kind of summarizing his first law in one word. So Newton here needs to get the last of this ketchup out of the bottle. If you've ever had like a glass bottle or even plastic ones, you know they settle to the bottom and you need to get it out. And just instinctively we shake it. So that's really Newton's first law in action. So in an attempt to get the last of the ketchup out of a glass bottle, Newton accelerates the bottle down. So we can see he's applying a force here and then quickly stops the bottle. So as a result, the ketchup in the bottle moves towards the opening. Explain why this works using Newton's first law. So really what we're saying here is Newton applies this force which causes the whole bottle to accelerate. Because the ketchup is in the bottle, it also accelerates from this applied force. And then Newton takes his hand, or what we do is we use our hand to stop the bottle, so we're applying another force in the opposite direction. And when that happens, that causes the bottle to accelerate in the opposite direction as well, which ultimately causes these two to cancel out and the bottle stops. But the ketchup has mass and therefore it has inertia as well. Since we are holding on to the bottle, when we stop the bottle, that's fine. We are applying a force to the bottle itself, which causes it to stop, right? That's the outside force that's changing this object's motion. But since the ketchup is not part of the bottle, the force isn't applied directly to it, right? We're applying the force to the bottle itself. And so as a result of that, without this force, the stopping force, or this force in the opposite direction, acting on the ketchup itself, the ketchup then continues to accelerate, which causes it to come out or move this way towards the top. And then you shake it a few times, and that's ultimately what happens. It comes down this way. So that's really Newton's first law. You see this in cars. There's a practice problem about that. That's ultimately how seatbelts work. So it's this Newton's first law is really this idea that an object will continue its state of motion. In this case, the ketchup has been given some velocity when it accelerates due to this original force, and it'll continue that way until some other force acts on it. So that's really Newton's first law. Thank you to our special guest, Chef Sir Isaac Newton. So on to his second law. Newton's second law says the acceleration of object is directly proportional to the net force acting on it and inversely proportional to the mass of the object. So we just did this in our last focus question. Focus question 2 was really about Newton's second law, or acceleration is equal to F, force divided by mass. So in this problem, two people are fighting over the last roll of toilet paper. If person A pulls on the 0.227 kilogram toilet paper roll with a force of 32 newtons to the left, and person B pulls on it with a force of 27 newtons to the right, what is the acceleration of the toilet paper? So we have to remember Newton's second law is always about net force. So what is the net force here? So in this case, F net is going to be equal to the force of person A, there we go. The force of person A and the force of person B, right? They're both applying a force to this. So F net is going to be Force of person A is minus 32 newtons, and force of person B is 27 newtons. Again, it's negative 32 because it's to the left, and positive 27 because it's to the right. So F net here is going to be equal to minus 5 newtons. We know the mass. They tell us the mass is 0.227 kilograms. So Newton's second law is acceleration is force divided by mass. So we're left with minus 5 newtons divided by 0.227 kilograms. So the acceleration of the toilet paper will be 5 divided by 0.227. We end up with negative 22.0 meters per second squared. So because this is negative, we know the object is going to accelerate to the left. We could probably figure that out just by looking at this problem originally. Since the greater force is to the left, we know that it'll accelerate to the left. We now can determine exactly at what rate it'll accelerate to the left, 22 meters per second. So this person wins the toilet paper war. Newton's third law. Newton's third law is kind of requires us to put a bunch of different things together. So we got to read this carefully. If two objects interact, the magnitude of the force exerted by object 1 on object 2 is equal in magnitude but opposite in direction of the force exerted by object 2 on object 1. In other words, for every action, there's an equal but opposite reaction. So what we need to understand here with Newton's third law is, in this problem, a student's kicking a soccer ball. So when they kick that soccer ball, we know that they're going to be applying a force right here. So the foot applies a force to the soccer ball. Newton's third law tells us that the soccer ball also applies a force that is equal to this force, but in the opposite direction. So this is the force of the foot on the soccer ball. This is the force of the soccer ball on the foot. If you watch the notes tutorial, we talked about normal force in there. So in this picture, right, Newton sitting on this chair applies the force down, that's his weight, and the chair pushes up with an equal and opposite force, and we call that equal and opposite force the normal force. So if you've ever kicked anything, you know that if it's a really massive object, it hurts, right? Even kicking a soccer ball, which isn't very massive, you still feel it. What are you feeling? You're feeling the force of the ball back on your foot. So back when sports were a thing, and before they were all canceled, I think this is something that everyone has experienced in some way, shape, or form. So these are the action-reaction pairs. So this would be the action force, and this would be the reaction force. The foot applies a force to the ball applies a reaction force that's equal but opposite. So that is Newton's third law. So the first question here, it gives us the information, the student's kicking the ball, the soccer ball has a mass of 0.4 kilograms, it's sitting at rest. 1 second after the force from the foot is applied, the ball has a velocity of 12 meters per second. They tell us the student's leg has a mass of 6 kilograms. So which object experiences a greater force? So the common mistake that we make here is thinking that this force is greater. The forces are equal. Newton's third law tells us the forces are equal but opposite. So we can write that mathematically by saying the force from the leg is equal to the opposite force from the ball. So in other words, whatever force the leg is applying to the football, the ball applies the same force back onto the foot, but it's in the opposite direction. So these forces are equal in magnitude, but opposite in direction. And so this is where we also have to we can put Newton's second law together with Newton's third law. So Newton's third law gives us this answer, which is the first one. Which experiences a greater force? Well, they experience the same force. So why is it? We know from experience if you kick a soccer ball in this case, the soccer ball goes flying, you do not. and why? Well, we can think of this as any force is equal to mass times acceleration. So this would be the mass of the leg times the acceleration of the leg. That's going to be equal to the opposite of the mass of the ball times the acceleration of the ball. Right? So I've just used Newton's second to describe force as mass times acceleration. So we can say that this is the same, this mass times acceleration is equal to the opposite of mass times acceleration is equal to this. Force of the leg equals the opposite of the force of the leg. So now that we've got this written out in this format, we can look at question 2, part 2. Does the player's leg accelerate? If so, at what rate? Well, the answer has to be yes, because if their leg did not accelerate and this was 0, then the force would be 0. And we know that the force isn't 0. So yes, the player's leg has to accelerate, right? Acceleration is change in velocity. So when you kick something, does your leg slow down? Yes. So therefore it's slowing down, its velocity is changing, it must therefore be accelerating. So what they're asking us for is, what is that rate? So they give us the mass of the leg, they give us the mass of the ball, they don't give us the acceleration of the ball, but they do give us some values about it. So we know that we can say that acceleration is equal to change in velocity over change in time. Or in other words, v final minus v initial divided by change in time. So in this problem, its final velocity is 12 meters per second. It starts at 0, and it takes 1 second to go from 0 meters per second to 12. So in other words, its acceleration is going to be 12 meters per second squared. So that is the acceleration of the soccer ball. So now I'm going to rearrange this first. So I'm looking for the acceleration of the leg. So really, I can say I would divide both sides by the mass of the leg. So acceleration of the leg is going to be equal to the opposite mass of the ball times acceleration of the ball divided by the mass of the leg. So that would be the mass of the ball. We need to not lose our direction here, so we keep the negative. The mass of the ball is 0.4 kilograms. Its acceleration we just determined is 12 meters per second squared. And the mass of the leg is 6 kilograms. So the acceleration of the leg is 0.4 times 12 divided by 6. It looks like this leg would be accelerating at 0.8 meters per second squared in the negative direction. So the leg would be slowing down. Its acceleration is 0.8 opposite due to this force, the force of the ball. So what's important to consider when we do Newton's third law here is forces are always equal. When two objects interact, doesn't matter. You could look at this as two people running into each other, right? A football player tackling another football player. If you have a 300-pound person tackling a 100-pound person, when they collide, the forces they experience are equal. That's the big idea. Newton's third law tells us the forces are equal in magnitude but opposite in direction. So then why is it that the 100-pound person goes flying and the 300-pound person does not? Well, it has to do with their masses, right? Different masses means different accelerations because these forces are equal. And that is the best way to think about Newton's third law. So I hope these are helpful as you work through the practice problems. Please, if you have questions or something doesn't make sense, shoot me an email and we can figure out how best to help you.